Section 4.2 Least Squares Regression. By the end of this lesson, we'll be able to find the least squares regression line, use the least squares regression line to make predictions, and interpret the slope and the y-intercept of the least squares regression line. We now know how to graphically describe the relation between two quantitative variables using a scatter diagram. We also have a numerical description of the strength of the linear relation between two quantitative variables, the correlation coefficient. If the correlation coefficient suggests a linear relation exists between two quantitative variables, it makes sense to find a linear equation that describes this relation. How can we find a linear equation that describes the relation between two variables? That is the purpose of this section. We will begin by simply selecting 2 points from a set of data and finding the equation of the line through these points. This method has many shortcomings that we point out through the next example. A word of caution is in order. The equation found in the next example is not the least squares regression line. So, for example, finding an equation that describes the linearly related data. Now, the data below in this table represent the club head speed and a distance a golf ball travels for 8 swings of the club. So if you notice here, the first column is the club head speed, which is the x explanatory variable, and you have your distance, which is the y. And then what we've done is we created a third column and created an order pair. So the order pair for the first one is 100, 257, and so on. Now, when you want to, in order to determine whether the equation describes linear related data, you're going to follow these steps. Step 1 is that you select 2 points so that a line drawn through the points appears to have a good fit. And we're going to call them x1, y1, x2, and y2. In step 2, we're going to find the slope of the line containing the 2 points using the slope formula, m is equal to y2 minus y1 over x2 minus x1. In step 3, we're now going to use the point slope formula, which is y minus y1, which is equal to m, which is the slope, times x minus x1, to find the equation of a line through the points selected in step 1. And then we're going to write the equation in the form of y equals mx plus b, where m is the slope and b is the y-intercept. So in step number 1, we're going to select 2 points. So in this particular example, the 2 points that we select for x1 and y1 is 99 and 258. And the other point, which is x2 and y2, 105, 75, 275. Okay, so in order to find the slope, we're going to take y2 and subtract y1 over x2 minus x1. So we know the following. We know that y2 is 275, and we know that y1 is 258. Okay, and then we're going to take x1, which is 105, and then we're going to subtract x1, which is 99. Okay, so 275 minus 258 gives us 17. 105 minus 99 gives us 6. So 17 divided by 6 gives us 2.8333. So that's going to represent our slope. So we found our slope by picking those 2 points. Step 3, now we're going to use the point slope formula to find the equation of the line and then write the equation in slope-intercept form. Okay, we'll recall that we found our slope to be 2.833. Okay, we're using x1 as our first point, which is 99, and we're using y1 to be 258. Okay, now recall that here is our point slope form, y minus y1, which is equal to m times x minus x1. So again, we have y1 here, we have our slope, and then we have x1. So the next step is to fill in that information. So it's going to be y minus 258 which is equal to m, which is a slope of 2.833, times x minus x1, which is 99. Okay, now the next step is we need to distribute our 2.833. So we're going to take 2.833, we're going to multiply it by x, and 2.833 and multiply it by 0.99. So when we do that, we get the following. So we get 2.833 3x minus 2.833 times 99 is 280.4969. And then we need to isolate y. So by isolating y, we're going to add 258 to both sides. So we're going to add 258 to both sides of this equation. So that means on this side we isolate, we have y, and that's going to equal 2.8333x minus 280.4967 plus 258.0000 gives us minus 22.4967. And so therefore, we now know what the slope is. We can say that the slope of our line, which is 2.833, so we know the slope of the line is 2.833. And then we've also determined that the y-intercept is minus 22.4967. So the y-intercept is negative 22.4967. Okay, so now we figured out what is the slope in the y-intercept. Okay, now in step 4, we want to be able to graph the line on a scatter diagram. So we want to find the 2 points that we have on a scatter diagram. Now recall where those 2 points are located. We know that this point here represents 99 and 258. And then the other point we have over here, which represents 105 and then 275. And those are the 2 points that we picked. So now what we want to do is we're going to create a line by just connecting those 2 points. So let's go ahead and do that. So we're going to connect those 2 points. So from here, we're going to connect that point, and there is our line. Okay, so let's go ahead and write our line. So what does that line represent? Well, this line represents the one we just found, which is y, which is equal to 2.833x minus 22.4967. Okay, and so now in step 5, we're now going to use the equation to predict the distance a golf ball will travel if the club head speed is 104 miles per hour. So again, that was the question it was asking. So here, what we're going to do is we're now going to choose a value for x in the question, and that question is telling us the following. It's saying that we're going to use, okay, the following value. So in our problem, it's asking us to predict. So this is the key word in here, predict, when the club head speed is 104 miles per hour. So that tells us that we're going to let x equal 104. And then we're going to plug it into this equation that we just found. So y is going to equal, now we're going to replace x to be 104. And so then we're going to do the following math. So we can do that on our calculator just to verify our answer. Okay. So let's go ahead and do that. So we're going to take 2.8333. We're going to multiply it by 104. And then we're going to subtract 22.4967. And then that gives us 272.1665. Rounding it to one decimal place gives us 272.2. So therefore we would say that y is now going to equal 272.2 yards. Okay. Now again, all we did was found a line of the data. Okay, this wasn't the LeastSquares regression line. Okay, this was just a line that we end up developing by picking 2 points, creating a line using the slope in the point slope form, and then using a number to predict what that value would be for the distance when we said that the club head speed would be 104. Okay, now we're going to move into objective 1. Okay, so what does objective 1 ask us to do here? Well, objective 1 is to find the least squares regression line and use the line to make predictions. Now, the line that we found in the previous example appears to describe the relation between club head speed and distance quite well. However, is there a line that fits the data better? Is there a line that fits the data best? Whenever we attempt to determine the best of something, we need a criterion for determining the best. For example, suppose that we are trying to identify the best domestic car. What do we mean by best? Best gas mileage? Best reliability? When finding the best line for describing the relation between two variables, we need a criterion for determining the best line. So we're going to consider the figure below. So again, this is what we have before. Okay, we have the figure where we have a line that we created from our previous example. Okay, so again, here's our distance and here's our club head speed. Okay, now, remember the equation that we found from the previous example. So the equation that we found from the previous example was the following. Okay, we found that this line, okay, we know that this line had the equation y, which is equal to 2.8333x minus 22.4967. Now, each y-coordinate on the line, okay, corresponds to a predicted distance for a given club head speed. So, for example, if a club head speed is 103 miles per hour, then the predicted distance is going to be the following. So what that means is we would then let x, okay, so we're going to say that x now is going to equal 103. So if we know the club head speed is 103, that means we're looking at this value on the x-axis. And then we're going to plug in that value, okay, for x into our equation. Okay, so that means we're going to get 2.8333 times 103 minus 22.4967, and that's going to give us 269.3 yards. Okay, so what that means here is that if we round this value okay, to 269.3, I want you to notice here is that there is our prediction. So this is the predicted value because we plugged it into the equation. So this represents the predicted value. Okay? And I want you to notice that there's something listed over here when we know what the predicted value is. So if we know that the predicted value in this question is 269.3, well, that's what we're going to substitute over here for the predicted value. Okay. Now, what is the observed value? Well, the observed value is the following. Well, the observed value is 274 because that was the actual point that was given in the scatter diagram for 103. And if you notice that 103 was the value that we got for that particular x value. So we chose that. So that means now we're going to find the observed and we're going to subtract the predicted value. And what that does is that gives us what we call a residual. So the residual is what we're finding. And what that means is the residual is what is the sort of value here that is the difference between these two y values. So by taking the observed, which is 274, the observed y value, and then subtracting the predicted 269.3, what it gives us is the residual of 4.7. So again, the observed distance for this club head speed is 274. The observed meaning that this is the actual point that we had on our graph. The difference between the observed and the predicted values. So remember, the difference between the observed and the predicted values of y is the error or residual. So we call that the error or residual. So again, for a club head speed of 103 miles per hour, the residual is the following. So again, we take the residual, and just to repeat this again, we take the observed y value, and then we're subtracting the predicted y value. And recall that the observed value is 274, and then we're subtracting the predicted value of 269.3 to give us 4.7 yards. So basically what it's saying here is that this value right here, okay, represents 4.7 because that is the distance between 274 and 269.3. So the residual for a club head speed of 103 miles per hour is represented in this figure by the length of the vertical line segment drawn between the point 103, 269.3 and 103 and 274. Now, the criterion to determine the line that best describes a relation between two variables is based on residuals. The most popular technique for making the residuals as small as possible is the method of least squares, developed by Adrian Marie Legendre. The least squares regression line minimizes the sum of the squared errors or residuals. The line minimizes the sum of the squared vertical distance between the observed values of y and those predicted by the line y hat. We represent this as minimize the sum of the residual squared. The advantage of the least squares criterion is that it allows for statistical inference on the predicted value and slope. We study this in more detail later in the course. Another advantage of the least squares criterion is explained by Legendre in the next Novelist Methodus pour la détermination des orbites des comités published in 1806. Of all the principles that can be proposed for this purpose, I think there is none more general, more exact, or easier to apply than that which we have used in this work. It consists of making the sum of squares of the errors a minimum. By this method, a kind of equilibrium is established among the errors which, since it prevents the extremes from dominating, is appropriate for revealing the state of the system which most nearly approaches the truth. Okay, now we're going to take a look at activity 1, which is what is the least squares? So I'm going to open up this applet, and it says this activity will allow you to visualize and understand the least squares regression criterion. So we're going to use this applet. So the first thing we want to do is we're going to click reset to remove all the points from the scatter diagram. Okay, so we're going to select reset, and it says create a scatter diagram with 8 points. So we're just going to select 8 points. Okay, so we'll just select 1 here, 2, 3, 4, 5, 6, 7, and then 8. Okay, so if you notice here, you can see that all these points form like a box around them, and there's a reason why it does that. And down below, you can see that it has an intercept at 10 of the green line, and then this SSE, and I'll talk more about that. Now, in part B, it's saying use the endpoints of the green line and attempt to fit a linear model to the data that minimizes the sum of the squared residuals or errors, which is SSE, which is this column over here. Now, if you notice that each point has a square whose side represents the residual point, the residual of the point. Therefore, the area of the square is the value of the squared residual, because the area of a square equals side squared. So your goal should be to make the sum of the areas of the squares as small as possible. The sum of the area of the squares is given under the heading SSE. So pay attention to the fit of the line versus the value of the sum of the squared residuals, or errors, which is SSE. So here is the green line. So I'm going to take this line and then I'm going to create sort of a line that best fits. So if we take a look here, okay, and then I'm going to take this endpoint. Okay, well, let's make it the best fit. And I want you to pay close attention to what's happening with the value in the lower right corner of the SSE here. Okay, so if we take this line to find the best fit, so I'm going to make it go through this point and maybe make it go through that point right there. You see the sum of the squares. Well, again, it's telling us that what it's telling us is that your goal should be to make the sum of the areas of the squares as small as possible. So we want that to be as small as possible. So the larger it is, it's not the line of best fit. If you go further away, again, it's getting bigger. So the closer we get here, which right now is about, let's see, 282. Let's see, is that the smallest one that we can get? We got 256, 248, 230, 20. So you can see here, this is giving us the line of best fit here. Okay, now, as we work with that, the next thing we want to do is we check the regression box, okay, which is the one in red down here, and we're going to compare the sum of the squared residuals for the green line to the least squares regression line. And notice that it is not possible to find a line whose sum of the squared residuals is less than a regression line. So let's click on this, and then you see there is the regression line. So regardless, okay, this regression line is the best fit. So no matter what, we're not going to get anything smaller than what that line is. So the regression line gives you the best fit, which is the one that's in red.